again, friends. Let's continue our discussion from where we left off. Last time we were discussing about dimensions and the application of dimensional analysis, and we have seen the principle of homogeneity and conversion of unit, how we convert one unit, one value from one system to another system. So the next part in the discussion is checking the correctness of an equation, checking the correctness or the dimensional consistency of an equation. Checking the correctness or dimensional consistency of an equation. So we are given an equation. Say there is S is equal to ut plus half at square. This is an equation, and we have to check whether it is dimensionally consistent or not. So you must have studied about this equation. Let's revise what this equation says. This S is distance. So in our dimensional analysis, distance is length. This U is speed. So last time we discussed the dimensional formula for speed. T for time, half is just a number, and A is acceleration. How acceleration is defined is speed upon time, and this T is again time, which is squared. Now, so in principle of homogeneity, we have seen that two quantities that are being added or subtracted must have same dimensions. So same type of quantities can be added, subtracted, or compared. So you can see there are two terms in this equation. One is ut and the other one is half at square. So these two terms must be dimensionally same. They should represent the same dimensional quantity. And in दोनों को हम S से compare कर रहे हैं. So S must also be the that means the dimension of S must be same as that ut and half at square. S की dimensions, ut की dimensions और half at square की dimensions, ये सारी dimensions same होनी चाहिए. If it is not so, then the equation is dimensionally inconsistent. So let us check whether it is dimensionally consistent or not. So in left hand side we have S, and the dimensional formula for S is distance, which is length. So dimensional formula for distance is L. And on the right hand side we have ut and half at square. So dimensional formula for ut plus dimensional formula for half at square. So the dimensional formula for speed, last time we have seen, it is Lt minus 1. So Lt minus 1, and this t is time. So one more t. And then in this part, half is a number which is dimensionless. It has no dimensions. So just the dimensional formula for A, which is Lt minus 2. Lt minus 2. And this t is squared, so time square. Okay, so here t raised to the power minus 1, and this t will cancel out, and you are left with of L. And here you can see minus 2 and plus 2, यहाँ पर भी time cancel हो जाएगा, and you are just left with L. So length plus length, L plus L. In dimensional analysis, length plus length is again length. So L plus L will be just L. So you can see that dimensions of the left hand side and dimensions of the right hand side are same. So this equation is dimensionally consistent. But this is not everything. This formula is only dimensionally consistent. Whether it is correct or not, I cannot say, or we cannot detect, since this number has no role in this dimensional analysis. इस नंबर की डायमेंशंस कहीं पर मेंशन नहीं हुई है. सो अगर इस नंबर को चेंज कर दिया जाए, से इस हाफ की जगह 1/3 लिखा हो, देन दैट फॉर्मूला इज नॉट करेक्ट. इस फॉर्मूले को जहां से हम डिराइव करते हैं, उस डेरिवेशन के बाद यहां पर 1/2 अपीयर होगा, हाफ अपीयर होगा. बट अगर 1/3 लिखा हुआ हो, सो दिस फॉर्मूला इज एक्चुअली इनकरेक्ट. बट अगर वो यहाँ पर 1/3 हो, सो उस डायमेंशनल एनालिसिस में उसका कोई रोल नहीं होगा, एंड स्टिल द लेफ्ट हैंड साइड एंड राइट हैंड साइड विल हैव सेम डायमेंशंस. So what's the conclusion? If a formula is dimensionally correct, it just may be correct. We cannot be sure that it is actually correct. It may be just correct. If there are numbers, if I change the value of numbers, the dimensional formula is still, the equation is still dimensionally consistent. But changing the numbers will change the equation. Will change the here. If half appears here, no other number can appear here. So if any formula is dimensionally correct, it may be correct. If it is dimensionally consistent, it may be correct. Now it is truly correct or not, we cannot tell. But if a formula is dimensionally incorrect, say if the dimensions of right hand side and left hand side are not same, if I put another t here, if I make this t cube, then you would find here t cube and t minus 2 and t plus 3. T raised to the minus 2 and t raised to a plus 3 will be just t. So in this part, you will be left with L and t. And since this is L and this is LT, so you cannot add them. एक part में length है, दूसरे part में LT है, so it is a different quantity, then different quantities को हम add नहीं कर सकते. That means कि ये formula dimensionally inconsistent हो जाएगा. So if a formula is dimensionally inconsistent, then surely we can say that it is incorrect. This is actually incorrect. So this checking the correctness will allow us to just check the dimensional consistency, and if it is dimensionally inconsistent, if a formula is dimensionally inconsistent, it is going to be actually incorrect. We can take one more example, a simple one. You know the formula for kinetic energy, K is equal to half mv square. K for kinetic energy, m for mass, and v is the speed. Now let's check the correctness. So on the left hand side we have kinetic energy. Last time we have seen that energy and work done have same dimensional formula. All types of energy will have same dimensional formula. So it will have the formula for work done, which is m L square and T minus 2. So the dimensional formula for kinetic energy is ml square T minus 2. And on the right hand side, the dimensional formula for half mv square, it is, now this half will have no role, so just mass, m for mass, and speed squared. Now if I square the speed, lt minus 1 whole square. Now this is m, and now here L squared, and t raised to the power minus 1 into 2 is minus 2. T raised to the power minus 2. So on the right hand side, the dimensional formula is ml squared t minus 2, which is same as the dimensional formula on the left hand side. So this formula is again dimensionally consistent, but you can clearly see, if I write 1 over 3 here, it is still going to be dimensionally consistent, but you know this is not the correct formula to calculate kinetic energy. Kinetic energy is half times mv square. It is not 1 by 3 mv square. So what do we find? That if a formula is dimensionally consistent, dimensionally correct, it may be actually correct. But if I say that the same kinetic energy formula is written as half m square and v square, then the right hand dimensions will be half m square v square. This will be, half will have no role, m squared and speed squared. So speed squared will be L square and t minus 2. So you can clearly see that this is not the same as the dimensions on the left hand side. Now this formula is dimensionally incorrect, and you can see that it is also actually incorrect. So if a formula is dimensionally incorrect, inconsistent, it is actually incorrect. So this is checking, this is how we check the correctness or dimensional consistency of an equation. And it's a good habit to check every dimensional formula that we derive, to check it dimensionally, to check its dimensional consistency. Whenever we derive a formula, it's a good habit to have to check the correctness, to check the dimensional consistency of the equation. So we will try to keep this practice, that after deriving every equation, we will check it dimensionally. we will check the dimensional consistency. Okay, so next part in the discussion is and this one is interesting one, deducing relation among different physical quantities. Deducing relations among different physical quantity. This is a very handy tool. So let's take an example, straight one. We know if a mass is suspended with the help of a string, say this is a small mass m, and it is suspended with the help of a string, this system is called simple pendulum. If I displace this mass slightly from its this position and release it, the mass will oscillate. This will perform a periodic motion. This will oscillate. So this is called a simple pendulum. Now we have to find the time period. Now what will be time period? Say if I release this mass from this position, then it will go to its previous position, and because of the speed it will go towards the other side, and then from there it will return and reach this position, and again it will come to the original position or the initial position. So the time for making this one oscillation, it comes from here to here and then from here to here and then comes back to the initial position. So the time for this one oscillation is called time period. So let's try to deduce a formula for this time period. The time period, let's try to find the time period depends on what quantities. Okay, so we will start from a pure guess. We will guess the time period depends on certain quantities. We don't have any other information. So just let's just get, say this is the length, this from this point to this point, the center of the bob is the length of the pendulum. So let's say the time period depends on the mass of the pendulum, and it depends on the length of the pendulum, and we can make a guess that it depends on the acceleration, the gravitational acceleration at the location. The gravitational acceleration is due to the attraction of the earth. So let's suppose that this time period also depends on the gravitational acceleration. Now we know, we are guessing that it just depends on mass. Now what is the relationship? It is inverse relationship or direct relationship, or it is proportional to m square, or inversely proportional to m square. We don't know. So we will write that this time period is proportional to m raised to some power. We don't know this number a. उसकी कौन से पावर के प्रोपोर्शनल है ये हमें यहाँ नहीं मालूम. उसकी इंफॉर्मेशन हम कहीं से नहीं निकाल सकते. And also it depends on length. So let's say it depends on L to the power b. And we have made a guess that it depends on gravitational acceleration. So let's say it depends on g to the power c. We can take many other quantities, suppose temperature or pressure, but for the sake of simplicity, let's settle with these values only. So the time period, we are guessing that time period depends on mass to some power a, and it depends on length to some power b, and g, it depends on g to some power c. So after this we can write that the proportionality constant will appear here. So let's write it k, and then m to the power a, L to the power b, and g to the power c. Now the dimensional consistency says that dimensions on the left hand side and right hand side must be same. If you are going to have a formula, the dimensions on the left and right hand sides should be same. So on the left hand side we have time period, and the dimensions of time period will be capital T. On the right hand side, this is a proportionality constant, and we suppose it has no dimensions. So m here, m raised to the power some number a, and this is length, so L raised to the power some number b, And this g is gravitational acceleration. It is due to gravitational force of Earth. So we have written a different symbol. Otherwise, this is just like any other acceleration. Dimensionally, it is simply any other acceleration. And dimensional formula for acceleration is Lt minus 2 and whole raised to the power c. Now collect the powers of different quantities. So m raised to the power, m appears only here. So m raised to the power a, and L has power b here and c here. So total power of L becomes b plus c, and t appears only here, so it has total power minus 2c. Okay, so now it looks like this. And on the left hand side there is no mass and time, so for that we can write m0, L0 and t raised to the power 1. Now if this formula is dimensionally correct, dimensionally consistent, dimensions अगर दोनों साइड में सेम है तो m की डायमेंशंस, m की जो पावर है दोनों साइड में वो भी सेम होनी चाहिए. अगर यहाँ पर m की पावर a है and यहाँ पर 0 है, that means a must be equal to 0. So we have find the value of a must be equal to 0. And here L has power b plus c, and here L has 0 power. So b plus c must be equal to 0, or this implies b will be equal to minus c. And this t has the dimensions minus 2c, and here it has dimension 1. So minus 2c must be equal to 1. Now minus 2c is equal to 1. From here we found the value of c, which is minus half. And if c is minus half, you can see b is minus c, and minus of minus half is just plus half. So b is plus half. So you found the values of all the exponents. A is 0, b is plus half, and c is minus half. Now I can put these values back in this equation here. So t will now look like k, the constant, and m has dimensions a, and a is 0. That means m will not appear. In this formula, m will not appear simply. And length to the power b, b has value plus half. So L to the power 1 over 2. And this g has power c, c is minus half, so g raised to the power minus half. And I can write it like this: L over g whole raised to the power 1 over 2. And this can also be written as k under root L over g. So the dimensional formula now looks like k under root L over g. L is length of the pendulum, g is gravitational constant, and you can see mass doesn't appear here. So we say that the time period of the sample pendulum does not depend on the mass of the bob. And you can notice one thing, that's I cannot calculate the value of k here. We don't have any tool in our calculation to find the value of k. And when we derive x by some other method, this k has a value 2 pi. But with this method, we are not able to find the value of k. So this is how we can deduce the formula for a physical quantity by pure guess. Let's take another example. I hope you have written everything down. So next example that we can look for, in circular motion, when an object moves on a circle, this is called circular motion. In a circular motion, the force on an object, let's try to calculate a formula for a force on an object moving on a circle. So say this object is moving on this circle, and say r is the radius of the circle, and this particle has a mass small m, and it is moving on a circle with speed v. So now we have to find a formula for force which is acting on this particle, on this circle. Again, we will guess. We will say that force on this m is directly proportional to mass of the particle, but we don't know to what power, to which power of mass, so we will write just A. We don't know the value of A now. And v to the power b, let's say it depends also on the speed, but which power we don't know, so I put a number b there, and also on the radius, so let's say r raised to the power c. Now the dimensional consistency says left hand side and right hand side both should have same dimensions. On left hand side we have force, and the dimensional formula for force, okay, a proportionality constant will also appear here. So let's say the proportionality constant is k, and then m raised to the power a, v raised to the power b, and r raised to the power c. Okay, now left hand side and right hand side, write the dimensional formula for left hand side and right hand side. For force, the dimensional formula is m l t minus 2, and I suppose that this k has no dimensions. Then the dimensional formula for mass and raised to the power a, then we have speed, which is l t minus 1, and it has power b, so total power b. Then you have radius. What is radius? It is simply length, distance, length. So for length we have L raised to the power c. Now collect the powers of different quantities on the right hand side. M is appearing only here, so it has total power a, and L is appearing at two places, it has power b and plus c. So L raised to the power b plus c, and T has powers minus b. T is appearing just at one place, so it has power minus b. Now, if it is dimensionally consistent, then dimensions on both sides should be same. That means, let's write this one more time. Okay, so here m has a power a, or dimension a, and here the dimension is 1. So a must be equal to 1. A is 1. And L has a power b plus c, and here it has a power 1, so b plus c must be equal to 1. And T has a power minus b here, and here it is minus 2, so minus b must be equal to minus 2, or simply b is equal to 2. Minus will cancel out from both sides. Now a is 1, b is 2, and from this equation, if you put the value of b here, you will find the value of c as minus 1. If 2 is here, then c is equal to minus 1. So you have got all the exponents. A is 1, b is 2, and c raised to the power minus 1. Now let's put these values in this expression. So the force formula will now look like k m raised to the power a is 1, so just m, and v raised to the power b is 2, so v squared, and r raised to the power c is minus 1, so r raised to the power minus 1, or I can write the same formula as m v square divided by r. So finally we have got formula for force. This is the formula for force acting on a particle that is moving on a circle. We call this force centripetal force. Again, you can see we are not able to find the value of this dimensional constant, and from other methods the value of k comes out to be 1. So to find the values of these proportionality constant, this formula is not, this method is not enough. But somehow we can have an idea how the formula will look like for a quantity that is depending on different other quantities. So this was deducing relation among different physical quantities. And the next part in the continuation is this one, designing a system of dimensions or units. Designing a system of dimensions or units. We are designing our own system. So we know that in SI system, the base quantities are mass, length and time, and there are 4 other quantities. But the dimensional analysis allows us to decide the base quantities. And in terms of those base quantity, we can calculate dimensional formula of any other physical quantity. For example, if we take the base quantities as velocity, time and force. If I say in my system of units, velocity, time and force are going to be the base units, then I want to know the dimensional formula for mass. In SI system, mass is base quantity and we calculate dimensional formula for velocity, time and force in terms of mass, length and time. But now I am deciding that velocity, time and force will be base units. Then what will be the dimensional formula for mass in such a system? So the dimensional analysis enables us to find such a relation. Okay, again, I would say that mass depends on velocity, it depends on time, it depends on force, but to what powers, I don't know. So I will put random numbers. So I'm saying that mass depends on velocity. Let's write V, small v for velocity, small t for time, and capital F for force. So I'm saying that mass depends on velocity. What power, I don't know, so I will put A. And it depends on time. What power? Let's call it B. And it depends on force. So let's write force raised to the power C. Now, the dimensional consistency will allow us to calculate the values of A, B, and C. So if this formula is dimensionally consistent, then dimensions on the left hand side and right hand side must be same. On the on the left hand side we have just mass. All the other quantities L and T are absent. So on the right hand side I can write M, L 0 and T is also 0. On the right hand side we have velocity, and the dimensional formula for velocity is Lt minus 1, and it has a power A. Then the dimensional formula for time is simply T, and it has a power B. And the dimensional formula for force is Mlt minus 2. Mlt minus 2, and it has a power C. So from here we can calculate the values of A, B and C, and then those values will be put here, will be put in this formula, and I can tell you that what is the dimensional formula of mass in terms of velocity, time and force. So let's continue. Let's collect the powers. On the right hand side, M is appearing here. It has a power total C. So M raised to the power C, and L is here and here. So it has power A and C. So A plus C. L has total power A plus C. And T is appearing at 3 places. So T has total power minus A and plus B and then minus 2C. Now, the dimensions on both sides should be same. So this C will be equal to 1. Here the power of mass is just 1, so C is going to be 1. Okay, we found C. Then L has power A plus C, and here L has power 0. So A plus C is 0, which says that A is equal to minus C, and C is 1 here, so A is minus 1. And T has power minus A plus B minus 2C, minus A plus B minus 2C, and on the left hand side it has 0, so this is equal to 0. Now put all the values. C is 1 and A is minus 1, so if you put minus 1 here it becomes 1, and plus B and minus 2C, C is equal to 1, so it is just minus 2, which is 0. So B comes out to be 1. The value of B is 1. So you have found all the exponents. A is minus 1, B is plus 1, and C is again plus 1. Now, if I want to write the formula of mass in terms of these base quantities, these chosen base quantities, then m will be equal to v raised to the power a is minus 1, so v raised to the power minus 1, and t raised to the power b is plus 1, so just t, and f raised to the power c is again plus 1, so just f. So in terms of these base quantities, the dimensional formula for mass will look like v raised to the power minus 1 t and f. So this is how we can choose any 1 unit or 2 unit or 3 units as base units, and then we can calculate dimensional formula for any physical quantity. Next, let's take one more example, and this example will have some interesting interpretation. Last time we calculated dimensional formula for Planck's constant, gravitational constant, Planck's constant small h, gravitational constant capital G, and speed of light. So speed of light is just any other speed. Dimensionally, speed of light or any speed is same. Now let us calculate dimensional formula of mass. Now let's choose these quantities, Planck's constant, gravitational constant, and c as base quantities, and let's derive a dimensional formula for the base quantities of SI units, that is mass, length, and time. So now we are going to derive a dimensional formula of mass, length, and time separately in terms of Planck's constant, gravitational constant, and speed of light, because these constants are very fundamental in nature. The Planck's constant is a fundamental constant in quantum mechanics. Gravitational constant is a fundamental universal constant in mechanics, or you can say gravitation. And speed of light is a fundamental constant in Einstein's theory. So let's derive a dimensional formula for mass in terms of these base quantities. So I have chosen base quantities as Planck's constant, gravitational constant, and speed of light. For speed of light we write c, speed of light in vacuum. And I have to find dimensional formula for mass in terms of these quantities. So I will again make a guess, and I will say that m is directly proportional to h raised to the power some a, and g raised to the power some b, and c, which is, okay, so I shouldn't be using ABC because C is being used for speed of light. So let's write the exponents as h raised to the power p, and g raised to the power q, and c raised to the power half. Okay. Now, so dimensions on the left hand side and right hand side should be same. Dimension on the left hand side is mass, and length and time are not there, so L0, T0. And on the right hand side we have dimensional formula for Planck's constant. So if you can remember, last time we calculated dimensional formula, this Planck's constant, which is m L square and t minus 1, and whole raised to the power p. Then the dimensional formula for gravitational constant, if you can recall, it is m raised to the power minus 1 L cube and t raised to the power minus 2, and this has whole power q. And then c is the speed, any other speed dimensionally same, so just Lt minus 1 for speed, and it has total power r. Now collect the dimensions, the powers on the right hand side. M is appearing at 2 places, so it has dimensions p and minus q. So m raised to the power total p minus q, and L is appearing at 3 places, so L has total power 2p and 3q plus 3q, and here it is r. So L has total power 2p plus 3q plus r, and T also appearing at 3 places, so it will have powers minus p and minus 2q, and here minus r. So the dimensions on the right hand side, p minus q for mass, and this is for length, and that is for time. Now dimensions should be same on both sides, so p minus q must be equal to 1. P minus Q must be equal to 1. Let's call this equation number 1. Then 2P plus 3Q, 2P plus 3Q plus R must be equal to 0. L has power 0. And let's call this equation 2. And then T has power minus 2Q and minus R, and T has power 0 on the left hand side, so it is 0. And let's call this equation 3. Now if you add equation 2 and equation 3, R, you can see R will be eliminated. So add equation 2 and equation 3, and it will give you, R will be cancelled out, and it will give you 2P minus P, which is just P. So this addition will give you just P, and 3Q minus 2Q, that is Q. So P plus Q is equal to, on the right hand side, 0 minus 0 is again 0, or 0 plus 0 is again 0. And the first equation is here, so let's write it again. P minus Q is 1. Now if I write these two equations, the Q will cancel out, and you will have 2P is equal to 1, or P is equal to half. So you found the value of P. Now if I write the value of P here, you can find the value of the value of Q, which is, if I put 1 here, it is going to be minus half, I think. Okay, let's put it. The value of P in equation 1. P is 1 and minus Q, and this is 1. So half will be subtracted from 1, and you will get Q as minus half. So the value of Q is minus half. Now you can put these values in either of these equations, and the value of the last term R will come out to be half again. So the value of P is plus half, Q is minus half, and R is plus half. Then the dimensional formula of mass in terms of these quantities will look like M will be equal to H raised to the power P, which has a value half, and G raised to the power Q, which has a value minus half, and C raised to the power R, which has a value plus half. So this will be the dimensional formula of mass if I choose H, G and C as base quantities. Now from here we can find how much will be 1 unit mass in terms of these chosen base quantities. So I can further write mass as H and C have plus half powers. So I can write it as H into C, and G has minus half power, so it will be in denominator. So HC over G, square root of HC over G will be the value of 1 unit mass. If I take 1 here, 1 unit mass, I call it MP. Let's call it MP. P for Planck's. So let's call this Planck mass. So 1 unit Planck mass, how much will be 1 unit Planck mass in this system? You can put the value of H, which is 6.6 into 10 raised to the power minus 34 joule second, and the value of C in vacuum is 3 into 10 raised to the power of 8. Let me write the values. H is 6.6 into 10 raised to the power 34 joule second. C has a value 3 into 10 raised to the power of 8 meter per second, and capital G has a value 6.67 into 10 raised to the power minus 11, and the unit is Newton meter square per kilogram square. We discussed it last time. Okay, so if I plug in these values here, you will get the value for MP as 5.44 into 10 raised to the power minus 8 kilogram. So 1 unit mass in such a system in which Planck's constant G and C are base units, 1 unit mass will be equal to 5.44 into 10 raised to the power minus 8 kilogram. Or we can say that Planck mass is 5.44 into 10 raised to the power minus 8 kilogram. Now, it has a very interesting interpretation. So let's note it down in one corner. The Planck's mass is 5.44 into 10 raised to the power minus 8 kilogram. Okay, so we just calculated dimensional formula for mass in terms of h, g and c. Now let's repeat the same calculation for length. Let's try to find the dimensional formula for length in terms of h, g and c. I hope you have noted it down. Now, this time we are going to derive dimensional formula of length in terms of h, g and c. So I would again say that L is directly proportional to h to the power some, now say x, and g to the power some y, and c to the power some z. Then dimensional consistency tells us that dimension on both sides should be equal. It has just L, so I can write M0, L and T0. On the right hand side, the dimensional formula for Planck's constant M L square T minus 1, which is a power x. Then gravitational constant M raised to the power minus 1, L cube and T raised to the power minus 2, total power y, and c is speed, which is Lt minus 1, total power z. Now collect the powers on the right hand side. M will have total power x minus y, this minus y, and no m there, so just m raised to the power x minus y. And L will have total power plus 2x and plus 3y, and here z, so plus z. Then time will have total power minus x from here and minus 2y and then minus z. Okay, now the dimensions on both sides should be same, so x minus y must be equal to 0. X minus y must be equal to 0. This is our first equation. Then 2x plus 3y plus z, 2x plus 3y plus z will be equal to 1, second equation. And then minus x minus 2y, this one, minus z will again be equal to 0, third equation. Now again, if I add these two equations, second and third, z will be eliminated and you are left off with 2x minus x, so just x, and then 3y minus 2y, so just plus y, and on the right hand side is now 1. So x plus y is equal to 1, and write the equation below this one. So x minus y is equal to 0. Now add these two, y will be eliminated and you will get the value of x. So 2x is equal to 1, or x is equal to half. The value of x is half. Then put the value of x here. You can see from this equation x will be equal to y, so y is also half. Y is plus half. And then put these values in either of these two equations and you will get the value of z, which comes out to be now minus 3 by 2. Z is minus 3 by 2. X is plus half, y is plus half, and z is minus 3 by 2. Now put these values in this equation and you will get the dimensional formula for length in terms of h, g and c. So the dimensional formula for length will be h raised to the power x, x is plus half, so h raised to the power half, g raised to the power y, which is again half, so g raised to the power half, and c raised to the power z. Now z is minus 3 by 2. Sorry, yes, so c raised to the power minus 3 by 2. So this is the dimensional formula for length in terms of h, g and c. And further you can calculate how much will be 1 unit length in this system. So let's write this LP, Planck length, and h G have powers plus half, so they will appear in numerator, H into G, and C has power minus 3 by 2. So I can write it like this, C cube. So the Planck length is square root of Hg over C cube. Now if you put the values of Hg and C, the number comes out to be, the Planck's length comes out to be 4.03 into 10 raised to the power minus 35, which is a very small length beyond any measurement. The Planck length is of order this. You can see when this number is either very large or very small, these factors will not matter much. So this is our Planck length. For interpretation, let's note it down here, 4.03 into 10 raised to the power minus 35 meter. So this is how we derive dimensional formula for length in terms of H, G and C, which we have taken as base units. Next, let's find it, let's do the same for time. Let's calculate Planck time. Okay, so I hope you have understood the things and we can do it more quickly. Now we have to find time. So time, let's say directly proportional to H raised to the power, again X, and G raised to the power Y, and C raised to the power Z. And dimensions on the both sides should be same. So M0, L0 and T, this is for time. And on the right hand side, H has dimensions ml square T minus 1 whole raised to the power X. G has dimensions m raised to the power minus 1 L cube and T minus 2 whole to the power Y. And C has dimensions LT minus 1 total power Z. Now collect the powers. Total power for M is X minus Y. X and minus Y. Then for L, total power is 2X and 3Y. So plus 3Y, and here it is Z. So plus Z. And T will have total power minus X and minus 2 from here, minus 2 and minus Z. Okay, so X minus Y will be 0. X minus Y is equal to 0, equation 1. So you can see from here X and Y will be same. Then 2X plus 3Y plus Z, this part will again be 0, second equation. And then minus X minus 2Y minus Z, minus X minus 2Y minus Z will be equal to 1, the dimension of time on the left hand side. Again, the same pattern appears. If you add equation 2 and equation 3, Z will be eliminated. So let's do 2X minus X is just X, and 3Y minus 2Y is just Y, which is equal to 1. Now we have this equation also, equation 1, X minus Y is equal to 0. From here you found the value of X as half. So value of X is half. Now, you know, from this equation, X and Y will be equal, so Y is also half. Y is also half. And put these values in either of these equations, and you will get the value of Z as minus 5 by 2. The value of Z is minus 5 by 2. Now write the dimensional formula for time in terms of H, G and C. The dimensional formula for time is H raised to the power X, which is half. So H raised to the power half, and G raised to the power Y, which is again half. So G raised to the power half, and C raised to the power Z. Z is minus 5 by 2. So C minus 5 by 2. C raised to the power minus 5 by 2. So this is the dimensional formula for time in terms of H, G, and C. And if you want to know 1 unit of time in that system, so let's write, we call this Planck time. It will be H and G both have power half, so I can write it as Hg, and C will be in denominator, sorry, this is G, capital G, C will be in denominator, which will have power 5. So Planck time is h, g and c raised to the power 5. Now if you plug in the values, the Planck time comes out to be 1.34 into 10 raised to the power minus 43 second. A very tiny mini time. This is Planck's time. 1.34 into 10 raised to the power minus 43 second. So let's note it down here. Planck time 1.34 into 10 raised to the power minus 43 second. Again, this number is very small, so this factor will not matter much. Now this has an interpretation. These numbers have an interpretation. We say it has many other interpretations, and one of them is that after the Big Bang, after the starting of the universe, after when universe just began, after that incident, so after this much time, after the Big Bang, after this time after the Big Bang, okay, so this much time after the Big Bang is called Planck time, and at this moment the length of the universe was this and mass of the universe was this. So now what are the other meanings of this interpretation? We will see along the course when we study something about modern physics like atomic structure or nuclei and the uncertainty principle and so on. So you will find what's the meaning, what's the further meaning of these. For now, we say this is Planck time, which is the time after the Big Bang, and at this moment the length of the universe was this and this was the mass of the universe. Okay, so this was our dimensional analysis. Now along the way you have seen that this dimensional analysis has some limitations. So let's down the limitations of dimensional analysis. Limitations of dimensional limitations. And one of the limitations you have seen that we are not able to find the value for proportionality constant. If any proportionality constant is appearing in the dimensional formula that we are deriving, we cannot find the value of that dimensional constant. So proportionality constant. The value of proportionality constant cannot be calculated by dimensional analysis. Second, we cannot find an expression in which a quantity has no dimension. For example, there is a quantity called refractive index. So let's write refractive index for n. It is defined as speed of light in vacuum divided by speed of light in any medium, air or oil or water or any other medium. So speed of light in numerator you have speed, in denominator you also have speed. So dimensionally these two expressions, if I write V over C, then dimensionally this is not different from this one. So अगर हम ये expression calculate करने की कोशिश करें, so we cannot find the value of ये हमें expression मिल जाएगा कि C और V का ratio है, but what is the order, कौन denominator में है कौन numerator में है, ये हम calculate नहीं कर सकते. So अगर किसी we are calculating a formula for a dimensionless quantity, then it will not be we will not be able to find the order of quantities, which one is appearing in numerator and which one is appearing in denominator, because these two are same. In numerator you have speed, in denominator you have speed. Here also you have speed in numerator and denominator, both are speeds. So in these calculations cannot be done. And if the formula contains non-algebraic terms, for example there is this equation A is equal to sine omega t. If non-algebraic terms are there, so I can tell you that this y depends on A, it depends on omega, it depends on, this letter is called omega, this is called angular frequency. So y depends on A, omega and t, whatever be the quantities, these quantities may be. But I cannot find that sine is also there. So if any non-algebraic term is appearing, dimensional formula will not produce that non-algebraic term. And next limitation, if your formula carries more than one term, for example, this equation s is equal to ut plus half at square. On the right hand side there are more than one term. So if a formula contains more than one term, this can also this formula can also not be calculated. We can calculate a formula in which there is just one term on both sides. If there are more than one terms, we are not able to find the formula. So these are some limitations. Still, dimensional analysis is very powerful, and it helps us in many ways. At least we will be able to check the dimensional consistency for every formula that we will derive. So this was dimensional analysis, and I hope you have taken some interest in this discussion. Next time we will discuss about errors and significant figures. Thank you very much, and see you next time.